Alright, so we were talking about Bluetooth, and Bluetooth uses frequency hopping. And basically they take 79 megahertz, divide them into 79 1 megahertz channels, and they switch the channel every 625 microseconds. And the only exception is that you don't switch the channel if you are in the middle of a transmission, and the transmission could be 1 slot long, 3 slot long, or 5 slot long, and that ensures that the master always speaks on the even slot and the slaves speak on the odd slots. Okay. And it is time division duplexing, which means that on the same, basically, when the master speaks, the slaves don't speak. When the slaves speak, when the master don't speak like that. Okay. All right. Any question on this point? This was the last slide we already finished. So I suppose you all know this one. Next question is, what does the packet look like? Packet is very short. 5 slots is only 3125 bits. 3125 bits. And so you could have a original packet which is bigger than that. Well, not bigger than that. Basically, the packet would be then in that case. Let's see, how does this work? Yeah, okay. Oh boy. So it has basically, this is the total 3125 bit packet if it is 5 slots long, and then the first 72 bits are access code, 54 bits are the header, and then the rest is payload. Obviously all of this will fit in 1 slot also if the payload was not very big. So what is there in the access code? The access code basically identifies the piconet. If you want to join a piconet, you put that access code in there, and otherwise if there are paging requests, which we'll discuss in a minute what paging is, and inquiries, and we will discuss that also. So there you put the access code, inquiry access code, that this is an inquiry about, if there is anybody around here, or paging who wants to join the network. Then the control header is only 18 bits long, but it is basically repeated 3 times. Or actually, anyway, it is encoded using 1/3 rate. So 18 bits are 3 bits of the member address. So everyone has a 3-bit address. So everybody actually starts with a 48-bit address, which you probably did in the homework. Was the homework about W? No, W. Okay, but anyway, Bluetooth, same thing. So you have 48-bit address, but then you come down to 3 bits when you join, because 48 bits would be too long to put into a small message like that. Okay, so when you join a network, you get a 3-bit address that you are number 7, 6, 4, 5, 3, whatever. And so that is the first thing in the header. Second thing is the type code. Type code is 4-bit long, and it explains whether it is a flow control. Type code will explain what kind of message it is. Flow control and ACK and NAC is 1 bit. Sequence number is, and the header error check is 8 bit. The total is 3 plus 4, 7 plus 1, 8 plus 8, 16 bit only. But where is 18 bit now? So let me just double check. 3 plus 4, 5, 1 is 8 plus 8. Maybe there is a 2-bit sequence number. So maybe I missed there 2 bits. So the total is 18 bits. Sequence number and header check could not be the same thing, because header HEC will cover rest of it. So I would guess that that is where the 2 bits go.
Isn't also 1 bit and the sequence number? only 3 plus 4.
Each of these are 1 bit, you think?
Yeah.
Okay, I will have to just check. And so, unless somebody is sure, we will just leave it undecided at this point. Somewhere, I mean, adding the numbers would be 18 bit total. And then you get 54 by multiplying by 3. And the reason you need such a high rate, so much multiplication, is basically the power is so low, and then basically we want to make sure that everybody is synchronized by that time, by the time the payload comes. Now there are 2 kinds of payload, synchronous and asynchronous. So remember, originally Bluetooth was invented for voice. All they wanted was a headset connected to a phone. It started by Ericsson, which is a phone making company. And so this was the main traffic, was a synchronous traffic. Synchronous traffic means that if you are talking every few slots, you will need a slot or 2, whatever. So the synchronous traffic has periodic reserved slots. Other slots can be allocated for asynchronous traffic. So other slots are on demand, which is basically the master will ask you, do you want to speak? And you say, yes, I want to speak, and then you get a slot, things like that. Okay? And so more details are coming up. But right now, in this slide, we want to make sure that we understand the packet format. And the key in the packet format is that the header is repeated 3 times, and that the access code basically explains whether it is a piconet or and who is being paged and inquiring. So we already used the word paging and inquiry. So this slide actually explains how the things works, but I think the better slide is the next one, which explains this in text. Okay. So we will be flipping between back and forth. So first of all, everybody starts on a standby, which they're not connected. And so master sends an inquiry and says that, okay, anybody wants to join? And then the players will send an inquiry response, and so it's like announcement, like a beacon from the base station in Wi-Fi. When somebody hears a beacon, they can say, okay, I want to join. So they will respond with their address and clock using CSMACA. CSMACA means there is a collision, and it is quite possible that your thing may not reach. So when you hear the next inquiry, you try again. Okay. The page state, so once your inquiry is received, then the master will send you a page message saying that, okay, you come and join me, and then you will get your address, and you will get exactly you can synchronize to the clock of that master, and so that is basically joining. So let's go back. So once you get to the page state, I'm still trying to figure out how this works. Okay, maybe it doesn't work. Once you get to the page state, from that you get connected. Once you are connected, then you can transmit. When you don't want to transmit, then you go on to sleep. Now there are 3 sleep states. Sleep states are hold, sniff, and park. Alright? So I'm going to explain those in the next slide. But before that, I just want to double confirm that everybody understand that the master sends the inquiry, and once your inquiry response is heard, then you get paged, and then you get connected. Okay, so very simple that way. Although this is very simple, later on it was discovered that this is too much. So they are going to reduce it even further. But yeah.
On the next slide, it says page message is sent in 3 consecutive slots, 3 frequencies. So is it 3 frequency hopping after each slot, or is it?
Right. Okay, so let me go back to this thing. This is basically this page message here, and the page message here, and the page message here. Those could be 3 different, because these are each 1 slot long. right? These are not 3 slot long message, right? So that is the normal hopping. And then this layer enters the page response state, and then in the exchange whatever basically, and then at the end they are all connected. And at the end you have 3-bit logical address. Now, the hold and sniff. So when you are on hold, you basically are not you are in some kind of semi-connected state. Basically, that means that your asynchronous traffic is disconnected. If you are on a phone, that continues. And since you are free for the other parts, you can do scanning, trying to find out if there are other Bluetooth things, or page and inquire, if you have those abilities. So anyway, so that is the hold state, is basically where you are awake but really not connected except for the synchronous traffic. A sniff is sleeping actively. Okay, it's like sitting in the class. That is different than sleeping on the bed, right? So a sniff is you are active. You might even have a connection going. You might have a data going transfer, but you want to sleep in middle because you don't want to waste energy. So that is a sniff state. Sorry, sniff is this one. And then park is you are really sleeping comfortably. Okay. When you park, you give up your 3-bit address. So then you get a 7-bit address because a lot of stations could be parked. 128 addresses, 128 stations could be parked. 7 have to be active. 7 people have to be in the, basically it's like this. 7 people have to be here in the class before the class. Not minimum, it's maximum. So that is basically 7 people can be a sniff or active, and the rest of them are in park or hold. Actually, I should correct that. Including the hold. 7 includes the hold. Okay? Because for SCO also you need a number, 3-bit number. So you have 3-bit number here, and you have 3-bit number here, and you have, if you are transmitting, obviously you have a 3-bit number. Now the question is, for park you don't have a 3-bit number, and if you are disconnected you don't have any number. Okay?
We have an 8-bit address for park, so that can be 255.
That can be 255. You're right. 8-bit is 256. Yeah. So 255 parked addresses. Thank you. All right. Now, how do you wake up? If somebody wants to reach you, then obviously they will let the master know, and then the master will probably want to reach you, and then the master will broadcast that in beacons, in periodic beacons, and it will repeat, many times. And so this is called a train of beacons. Yeah.
When it wakes up, does it get the 3-bit number again? Or?
Yeah. So if from park, when you go to sniff, you have to go back to a new 3-bit number, because it might have been given to somebody else. So that's the thing. You don't want to go to park if you are active really, because it takes a long time to wake up, right? And from here, it is really not sleeping. It is, saving energy. Okay. So let's see. You are using GPS and Bluetooth. It kind of keeps shifting between the park, so between the sniff and active, sniff and active, sniff and active. Even though you don't see that part, it is continuously active, but it is sniffing all the time. Is that clear? Okay. On the other hand, you are using a headset, and then you don't have any phone call, nothing. At that point, it is parked, or maybe even disconnected. But when the phone call comes, then you get into the transmitting and a sniff kind of state. Yeah.
So the GPS will say that there's 255 total slaves in the system, or is there enough?
Disconnected. So the thing is, yeah, park, actually here I think, first of all, even 7 is too big a number. You don't talk to 7 devices at a time right now. Soon you will, in the next few slides I will show you how. But right now you talk one thing at a time, right? 255 parked. I think we need something really big application where one thing is talking to 255 things, and there are applications coming up like that. Okay, so these are the extreme numbers that they could think at the time when it was designed, and that is 1990s, 20 years ago. Does that answer your question? Did I interrupt you in the middle?
Yeah.
Okay, all right. So 255 is the maximum people who can be connected and maybe sleeping or whatever, right? But generally we never reach that number. Yeah.
Hypothetically, if there were 7 slaves and there were some parts, how would they be able to see an active number?
Of course, they will not get eighth one will not come in. So somebody will have to go to sleep. So you think these were extremes, they thought that 7 people is just too much, which was at that time, but now we are running out of that. So I will show you the applications at the end. Alright, the protocol stack. Now here's another thing different about the Bluetooth than other protocols that we have seen so far. So I put this stack here. And that is that it covers everything from PHY to applications. It doesn't go through IP. It doesn't worry about the OSI model. It has everything from PHY, and it has its own names. And you can see right now we can count 1, 2, 3, 4, 5, 6 layers. So it is not 7 or 5. Okay. And so the layers have different meanings than before. Basically RF, as you can see, RF is radio frequency. That is simply the modulation layer, frequency hopping, and GFSK modulation. So I will tell you what is GFSK. Actually, it is, just hold on to that thought because I have a picture which shows you GFSK later on. So anyway, so GFSK modulation is done here, and the frequency hopping. So this layer is responsible for, clock changing on the clock. Baseband is also, in that sense, half of PHY and half of MAC in some sense, because it does the frequency hop selection, connection, and then the MAC. MAC is the immediate access control. So that is into this one. So this is pure radio, and this is some computation and things like that, right? Baseband. Then there's a link manager, more of a management thing. On the side you have L2 cap. So L2 cap is basically logical link. L2 is LL cap actually. Logical link. So this is very similar to what we have LLC. If you remember LLC in IEEE, goes just above the MAC. And so that what it allows you to multiplex many protocols into one. Okay, one MAC. So this is logical link is simply protocol multiplexing. Then there are many protocols that you can use, and then on the top of these protocols there are applications. Now there is another interesting thing is that the number of applications is fixed. You cannot just write an application for Bluetooth. Bluetooth people write the applications. And so they said, well, if they write an application for headset, everybody has to implement that code. Okay, so they call it profiles. So there are profiles, and in the beginning there were 13 profiles, so you could use Bluetooth for 13 things, such as headset or GPS. You could think of any of the original applications that you can think of that you used your Bluetooth with. That was the thing with those were the profiles. Now the protocols here are SDP, and these are all explained in the slide here. So I'm going to hold on to that thought for a minute. But before I get out of this slide, and I will keep coming back to this in the next 2 slides, I want to explain the addressing part. Everybody has a 14-bit address, 48-bit address. And out of that, you take the 24-bit address, and that is called the lower address part, LAP. And 8-bit is called UAP, upper address part, LAP and UAP. And in the middle is non-significant, don't care kind of part. Okay, so 48-bit. Now you know that the first 22, actually the first 2 bits are universal and multicast bits, and then 22 bits are OUI. OUI is organizational unique identifier. Anybody knows what is OUI? 22-bit OUI in IEEE addresses. I'm sure I discussed in this class, and this is also discussed in 473. This is very fundamental. 48-bit addresses consist of what? If you go to IEEE, what do you get? Anybody remembers that? Nobody remembers that.
OUI is assigned to the organization.
Yeah, to the manufacturer. So this is what happens. If you manufacture anything which needs this address, you have to go to IEEE and get the address. And IEEE gives you 2 raised to 10 addresses at a time. 1064, maybe more. I don't know. Maybe they can give you more. 2 raised to 24 addresses at a time. Okay, they can give you 2 raised to 24 addresses at a time. And so they tell you that, okay, so just take these first 24 bits, and then you can use the last 24 bits whatever you want. Generally, people start with 0 and then increment by 1 and everything. Okay. If you start a new company like we did, Nana Networks, we got an IEEE code. So the first part is called Organizationally Unique Identifier, OUI. By looking at the first 24 bit, you can tell who made the chip. If you buy any Wi-Fi device, or any Wi-Fi or any IEEE address device, which includes Ethernet, includes 16, 14, 13, 15, whatever we have discussed here in the class 802, whatever, they all have 48-bit addresses, and the 22 bits indicate who made the chip. Whether it is Broadcom, and there are many other manufacturers who make the chip. I'm coming to your question. So we can figure out who made the chip because it is burned into the chip. The address is burned into the chip. It's not somebody can write into the chip. So it is burned into the chip. And so the 22 bit, so if you go to the internet, if you put OUI and whatever the OUI is, it can probably tell you what Google can tell you who made the chip. And so that is the OUI part. All right. UAP plus NAP. Now, having said that, OUI is only 22 bits because the first 2 bits are not really nothing to do with the organization. First bit tells you whether it is multicast or multicast or unicast, and second bit tells you whether it is global or local. Right? So the first 2 bits are not in the organization's control, but the 22 bits are. Okay? Yeah, go ahead.
I was going to answer it, but I was going to ask how you ensure that different organizations use other organizations.
Oh yeah, so this has not happened yet. I mean, in the sense that somebody, in China, Pakistan, or Russia could put some American Apple address and then say, okay, this is made by Apple. Hopefully it has not happened, so far. I mean, there is a possibility of everything like that, but at the organization level, this has not happened. Okay? And I don't know if there is an advantage to it, because it doesn't really cost anything. I mean, if you pay just $1,000 and you get 10 to 24 addresses, you are happy for life. Why would you want to steal somebody else's? It's $1,000 for 10 to 24. All right. So it's easy to get right now. At least, I mean, it was easy to get in 2000 when we tried it. But I mean, I'm sure that they have not run out of it. But having said that, yes, there is a possibility of somebody hacking, somebody trying to put a denial. Actually, it is very easy to do denial of service attack, by the way. Even though this is burned into the chip, most of the routers today allow you to override that. Okay, so all the routers that I have, they say, okay, do you want to Yeah, you want to clone your MAC address. Clone your MAC address, and that's what we have to do. So my laptop MAC address goes to the router, and that's how it connects to the hotel. All right, because the hotel only allows one MAC address, so people know how to cheat that. I mean, like basically, my MAC address is, I have this laptop and then that laptop and then that laptop, so I connect to the router, and then I connect to the router at all, everything, right? So that's what it is. Every router allows. That's kind of a standard feature nowadays, cloning the MAC address. Okay. All right. So much about the addresses. All right. There's nothing else here. All right. So about the L2 cap, we already said that this protocol, multiplexing and reassembly, etc. And then the host controller interface. This interface basically ensures that whatever you speak, and I don't understand why it is sitting here. It should be sitting more like here, so that everybody goes to host controller interface. This is one that provides common interface to all regardless of the hardware. So the hardware could be manufactured by many different vendors. This RF and baseband could be by many different vendors, but this will ensure that the interface is same. So everything should go like this, okay, through the host controller interface. RF comm layer, the radio frequency communication layer, it is simply a serial port. So there are few things that were very common in those days, in 1990s. 1990s, all the IOs was done through a serial port. Anybody has seen a serial port, or anybody has not seen a serial port? Everybody has seen a serial port. 25 pin port. No, serial port was only 9 pin, I think. Parallel port was 25 pin. Right? Everybody has seen those serial and parallel ports. They are no longer there in any computer, but they used to be in the laptops and desktops and everything else. So those ports are emulated here. Another thing used to be common was infrared port. So if you wanted to send something, you will use infrared, which is like a remote control thing, right? So that was emulated here. Telephony is already common. So those are the protocols here. You will see one by one. So RF communication layer, that produces a serial port. So if you have written any program that requires a serial port, you use that program on the top of this protocol, RF communication protocol. Basically, you will get a virtual serial port, and then you will say, I'm connected. I think they used to be called COM, COM1, COM2, COM3, COM4, COM7. So you just connect to some COM number that will be assigned. That is RF COM. Service discovery protocol is basically, as the name indicates, basically to find out if you have headset GPS available around here or not. And then this is a new protocol. I just recently saw this, actually, for the first time. Bluetooth network encapsulation protocol. Now, finally, they woke up to the idea that lot of I/O is done through Ethernet nowadays, and not through serial port, and Ethernet and IP. So now they invented this protocol, BNEP, and which I put into the picture here. You will not find this in many books. BNEP protocol's idea is to just take the IP and Ethernet and somehow send it through Bluetooth. All right, TCS. TCS is coming up. TCS is actually here. TCS is the telephony control specification binary. So this is call control. So there are two parts of telephones. One is that when you send a ringing to a phone, that's a call control. When somebody picks up the phone, that's a call control. A message is sent back that, okay, they have picked up the phone. When you start talking, that is audio. That is like a data plane. So the control plane is here. Telephony control goes to TCS. So that goes to this one. Audio is carried over the SCO. So that one is this part here. This is the synchronous thing. It doesn't go through any of this. You get certain slots, and in those slots you can just go over and out. Okay? Audio. And then IRDA. IRDA is that infrared. So infrared if you had infrared application that use infrared, just similar to COM port, you would get this thing, IRDA protocol. They are not shown in this picture here, but they would fit somewhere here too. I mean, basically, so there is IRDA profile as well. Okay, Alex, IRDA. So there is a IRDA applications, and then there is IRDA object exchange, etc., etc. So finally, at the end is application profile, which is basically what can you do with this Bluetooth. And these are standard profiles: headset, cardless telephony, intercom, LAN, blah, blah, blah. Now, this was the idea that we are not designing a protocol for general use like Ethernet. We are designing a protocol for a very specific use. And they wanted to make sure that the protocol does not fail in practice. So that means they wanted to have extreme what we call interoperability. You could buy the headset from any company, you could buy the phone from any company, and this would be able to talk Bluetooth. If they didn't, that would be a real problem, right? So they made sure that there are only certain applications that can run on it, and those applications were standardized, and those are called profiles. Okay? And there were 13 in the beginning, now the list has grown up. So they had complete control from bottom to the top. And that actually may be a reason for success. Bluetooth has been successful. I mean, today you cannot imagine life without Bluetooth. I try to turn off my Bluetooth once in a while, and I will show you why, tell you later on why, but then I have to turn it on again. So, so the idea is that the Bluetooth has been successful, and they are trying to build on that success, as we'll see later. Here's some of the recent list of profiles: headset, GPS, hands-free, phone book access, SIM access, synchronization, video distribution, blood pressure, and they went on and on and on until they ran out of space. This is not the complete list. All right. So the final issue is how much power is required. And Bluetooth actually is a low power technology. So you can see that 11B gives you 11 megabits and uses 15 milliwatts, 50 milliwatts. And if you calculate, how much energy you use per bit, you will come up with that it uses 36.4 millijoules per megabyte. Okay. And then the rest of the list you can see 11G, there's only 7.4, 11A, that's 29.6, Bluetooth does 8.0, and 15.3, which we haven't talked about, does 0.03. So this woke up Bluetooth, that they are low but not really the lowest. And their ideal goal was to be the low power, right? And then they realized that they have a problem. And the problem was that they have connections, which they should not. Once connected the Bluetooth Classic, now they call it Bluetooth Classic because there's a new version I'm going to talk about in a minute, right? Bluetooth Classic maintains connections even when there is no data. So even, like you're sniffing and all that, that is wasting energy. And so it's not low enough. Okay, so then they have to discover a method where they don't need to connect. Any questions? Right, but before I go into the next version of Bluetooth, which is the latest version, I wanted to tell you how Bluetooth and Wi-Fi live together. Okay, and this problem actually has been solved by IEEE itself by having a standard. Basically, because both Bluetooth and Wi-Fi, Bluetooth started life as 802.15.1, was it 1? And Wi-Fi is 11. So basically, they from the same organization, same people, and a set of people or similar set of people go there. So and all the laptops, etc., have to implement both at the same time. So they decided, how do we do it? Now the difference is that Wi-Fi uses only 20 megahertz at a time. It used to, at least in the beginning. And Bluetooth uses the whole 79 megahertz, sorry, 20 megahertz and 79 megahertz. Right? Everybody agrees with that? All right. So the question is, how do we avoid each other, clashing with each other? And so there are two sets of strategies. One is collaborative strategy. Okay, collaborative strategies, which means that the two networks on the same device. If you are on the same chip or on the same computer, you can at least talk to each other and say, okay, I am talking, you don't talk, please. All right? And the second is non-collaborative strategies. Okay, where there is a Bluetooth in that phone and then there is a Wi-Fi on my computer. They can interfere. How can they avoid each other, right? So the first one is collaborative, which is kind of always implemented now. One is that we could do time division. Is that Bluetooth skips the slots when Wi-Fi is busy. So Bluetooth goes slot by slot by slot, and in each slot it checks whether Wi-Fi is there or not. Right? And if the Wi-Fi is there, the Bluetooth skips it. And if the Bluetooth is continuing, let's say 5 slots, then the Wi-Fi skips it. So they both, do some kind of what you call carrier sense, and then they do multiple access, right? So that fixes it. And then Wi-Fi actually has this time allocation where they have time allocated for fixed them access. Remember that we had contention mode and non-contention mode in Wi-Fi. So Wi-Fi could even reserve some time. Okay, every this one cycle, this much time I'm going to reserve for Bluetooth. All right. Second thing is packet traffic arbitration. And since the two are not equally active, Wi-Fi is a lot more active on my computer than Bluetooth. Another alternative is that we put both of them on the same queue, and whenever the Bluetooth packet comes to the head, Bluetooth takes over. Whenever the Wi-Fi packet comes to the head, Wi-Fi takes over. Okay, so that way you don't have to reserve slots for no use. And third method is notch filter. Notch filter is that Wi-Fi uses 20 megahertz but uses OFDM, right? So it could figure out that Bluetooth is using this particular megahertz right now, and that megahertz it could just take out and use the rest of it, right? So frequency that one. And similarly, the Bluetooth could do something is that the Bluetooth could check that it looks like there is a lot of noise on this particular megahertz and not use that one, skip it out. And that is actually coming up, that is called adaptive frequency hopping. And so in later version, they adapted that as well. All right. So if you are on the same device, it is easy to manage. Everybody understand these three methods? Time sharing, frequency sharing, or packet sharing. Queue sharing, right? Three methods. Now, if you're not on the same device, then you don't know when they will be transmitting, when you will be transmitting. Then you have these methods. Basically, these methods are based upon measurement of noise, figuring out when somebody is transmitting. So, adaptive packet selection. So, the Bluetooth, if it sees a lot of noise, then it changes its FEC rate or modulation. FEC rate, remember that 1/3 business. That can be changed to a higher FEC and use FEC only if there is a noise. No FEC if there is no interference. No FEC if no interference. No FEC if no interference, right? Otherwise it will be bad. Then master delay policy. Bluetooth keeps track of error states on various frequencies. So it goes to 79 different different channels, but then it knows that some channels are bad, and those channels it just actually the same thing as adaptive frequency hopping. So adaptive frequency hopping is exactly the same thing. Hop only over good frequencies. So bad frequencies are measured, and then they are announced that we don't hop over those. And then adaptive notch filter on Wi-Fi, and Wi-Fi can do the same thing. Wi-Fi can basically figure out, well, so they can figure it out for 625 microsecond, because Wi-Fi will, the Bluetooth will jump over to some other frequency. But in the first 625 microsecond, if within the few bits Wi-Fi finds out that there's a lot of noise, it can just remove those carriers. So this is also very similar to the previous one. We can do frequency, actually most of it is actually frequency shifting in some sense. And then second thing is this FEC. Those are the only two things here. All right. So now what we have finished so far is what we call Bluetooth original, or Bluetooth classic, or Bluetooth basic rate. Okay, and that's what most of the devices that you have, unless you bought something in the last 2-3 years, which many of you did, they have that. If you have something which is, let's say, iOS 7 or something, that has next version of Bluetooth, and I'm going to talk about that. So the Bluetooth was happy so far, and they kept increasing, making Bluetooth better, and the better really meant was more data rate. So there is a Bluetooth 2, Bluetooth 3, which we'll not talk about, and all they did there was increase data rate from 700 kilobits to all the way to 24 megabits. All right, but that is not really significant change. Some changes in the modulation. The real change came when people started thinking about Internet of Things. And so Internet of Things simply, I will have a full lecture on Internet of Things, but for the start time being, you want everything that is on your body to be connected, your watch, your glasses, your phone, your heart monitor, your whatever, GPS, everything to be connected together into a network. So that is Internet of Things right there. And there are other things that can be connected too. And some of these things are very simple. So, for example, your heart rate monitor doesn't really need to say anything. It just says, okay, your monitor rate is 67 pulses a minute or whatever. I don't even know the exact unit. So the thermometer might say 30 degree Fahrenheit, and it will just keep repeating that every few minutes or every few hours or so on and so forth, right? But you need that to be connected so that you can read it remotely, you can control it remotely, and so on and so forth, right? So we need networking technology for such simple things. And the task is very simple. All I want to say is one number. And then I want to go back to sleep. Or, your speedometer says you're running at 55 kilometers per hour. Right? Or your energy meter says that you are at 23 kilowatt hour. So these are very simple announcements, and they happen on either they could happen on event triggered, means when the temperature changes it could announce, or when the speed changes it could announce, or it could be just clock ticks every minute they could announce, or they could be polled when asked. And so the thing is, these things should be very simple, and they need protocol that is very simple, and they don't need to worry about IP, because somebody else could speak IP for them. And that was the idea, is that not every single device, so your heart rate monitor doesn't have to speak IP. As long as it can speak to your phone can speak IP. Right? So it doesn't have to worry about routing and multi-hop and global addressing and things like that. So that's the idea. Okay, this is called a state announcement. So now there is a new version of Bluetooth called Bluetooth Smart. They called it Bluetooth Low Energy first, but I think after some brand marketing, they figured out that this one is better for general public. They don't understand low energy; they understand smart. Okay, I don't know why it is smart, but this is the name finally selected. Bluetooth Smart. It's actually low energy. So what is low energy? It consumes 1% of the classic. 1% to 50% of classic. And it is designed for very short broadcast. We already took those examples like, heart rate, body temperatures, variables, automobile, and there are so many applications. And it was not designed for voice, video, and file transfer. Okay, so they're not talking about, 5 megabits per second or 55 megabits per second. They're just, small. Yeah.
So how would you do, like, phone calls with the Bluetooth? Would you use the passive?
Yeah, right. So how would you do phone calls? So this is not designed for phone call. And so you already brought up a point which is coming up in the last line. This is a new protocol design, totally incompatible with the previous Bluetooth. And you will have two Bluetooths in your device. Bluetooth Classic, which they call it Bluetooth Basic Rate, and Bluetooth Smart. Bluetooth Smart will do this job, and Bluetooth Classic will do your phone calls. Alright, because if we change one, it doesn't work for the other. Okay, connections are bad, so they didn't want to have a 3-way handshake and 4-way handshakes and disconnect and this and that. Just say hello and gone. Alright, so small messages, throughput is not important. Battery life is the most important thing, because most of these things, such as your watch, you don't change the battery for months, right? And your heart rate monitor, you don't want to change battery for years and things like that, right? So that was the key, is the battery. Simple. So we don't want any routing and stuff, nothing like that. You just want to talk to one device and go to sleep. Lower cost than Bluetooth Classic. Obviously, since these would be in billions, these Internet of Things, we don't want, we want the cost to be low, really low. So basically, they took a new protocol design based upon Nokia's BiBri technology. It is interesting that Nokia's BiBri technology is dated the same as the original Bluetooth. Original Bluetooth is 1990, BiBri is 1990 technology. However, at that time, it was rejected by the Bluetooth committee. Now it has been accepted as the next generation. Interesting, And so now the good thing is that they have implemented these both, and they found out that if you implement both of them on the same chip, the extra hardware is not that much. Even though the technology is different, there is a lot of commonality. The commonality is that the new one, as we will see in a minute, also uses frequency hopping. All right. And therefore, the hardware part is, that is what goes in the lowest, remember RF layer, that is common, right? So the cost is not very much. So first they thought maybe people will have two kinds of Bluetooth, Bluetooth Smart and Bluetooth Basic Rate. And then they said, and so there were some chips which were made that way. Two different chips, but then somebody implemented together and they said, no, you don't need to make one chip. So now everything that you will get from now on would be combined thing, right? And that's what I said, iOS 7, if you have the iPhone 5 and whatever, the latest iPhone, you get that built in. All right. Now the Smart PHY. Smart PHY uses the same 2.4 gigahertz. It uses the same topology. It uses Gaussian frequency shift keying, the same as before. And so I explain here Gaussian. What is Gaussian about it is that normally if you shift the frequency, now remember this is frequency, not the amplitude. So you will go to one frequency, then you will shift to some other frequency, then you will shift some other. It doesn't have to be a square like this. It could be here, there, then go up there, and then come down there, and so on and so forth, right? So the frequency could be anywhere on the 79 channels, not binary like this. I've just taken a simple example of binary frequency shift. Now, the problem with this is that if you do a sudden change in frequency, that produces a lot more overflow in the band, okay, out of the band signal. However, if you do a very smooth change, So when you want to go from zero, I mean not zero, whatever frequency to here, you go slowly using a Gaussian curve, and then you come down slowly using Gaussian curve. It's the same thing, except that it is much more, overflow is very little. Okay, so this is kind of a standard practice. Whenever you do frequency shift, you do it slowly and not jump. Okay, and whenever you sense, obviously you are not going to sense from the beginning. What happens? It takes several thousand cycles to figure out what frequency you are at. Right? You are 2.4 gigahertz. So 2.4 gigahertz means 2.4 billion cycles per second. Right? And so you take about 1,000 cycles. That's not a big deal. To figure out whether this is the frequency. So you don't figure it out right at the beginning. You figure it out, somewhat in the middle, what frequency you are at. Okay. So anyway, that is Gaussian frequency shift keying. And the reason we use that is to avoid the overflow. Now, instead of 1 megahertz, they did change the frequency to 2 megahertz. Okay. And I couldn't find the reason for that. But anyway, so now instead of 79, they have 40 channels with 2 megahertz spacing. And the second change they made was that instead of going all over equally, they selected 3 channels which are special. Okay. These 3 channels are reserved for advertising. So basically, when you're looking for a new network, you don't go over all 79 channels, you go to one of these 3. When you want to announce yourself you don't announce everywhere, you announce on these 3. So that reduces the energy consumption, because otherwise to find a partner, you will have to say 79 times and hopefully hit the partner at the same time, right? Now with the 3, it's much easier. Okay. So it makes sense to have a smaller number of channels for finding. Once we have found each other, then we could talk on 79, actually 37 channels here. So out of 40, 3 channels are reserved for advertising and 37 channels are reserved for data. Now, these 3 channels are not 1, 2, 3. They are here, here, and here, but they are numbered like this: 37, 38, 39. Okay. The others are numbered 0, 1, 2, 3, 4, 5, 6, all the way up to 36, 0 to 36. So 37 channels for data and 3 channels for advertising. And they are called 37, 38, and 39. And so these channels were selected because generally Wi-Fi's avoid these channels. Now I haven't done the calculation, but you can do the calculation that if Wi-Fi is working on 20 megahertz, the Wi-Fi uses channel 1, right? Channel 1 goes from, I think it skips the very first 5 megahertz. Now I'm not sure. I have to go back to the channel diagram. And then it goes up to some number, right? So this one appears right in the middle between 1 and 6. And this is just before 1. And this is just the last one. So these are the least congested channels, or least congested spaces in that band, 2.4 gigahertz band. So these were selected for that, okay? So this is the phi difference. The phi difference is mainly that instead of 1 megahertz, they have 2 megahertz, and then they have 3 advertising channels. The Mac, they have a similar simplification, or you want to call it, is that you could just advertise. Basically, there are two kinds of devices. First is peripheral and central. Peripheral devices are very simple, just like Wi-Fi selected base stations and the stations. Bluetooth originally had peer-to-peer. Both devices were identical. Right? Anybody could become a master, anybody could become a slave. But now, with this Bluetooth Smart, there is a real master which we call central, right? And there is a slave which we call peripheral. And there are two kinds of PDUs, packets, advertising and data. Now, advertising can be done anytime, and advertising could be one of these four things. It could be non-connectable advertising. So it could just simply say 37 degrees centigrade. That's it. You don't have to do any connection. Just announce and go back to sleep. If somebody is listening, fine. If somebody is not listening, fine. I don't care. Right? That's the thermometer. And that's all it needs to do is tell the temperature. If nobody is reading, it doesn't care. So that is the first thing. Non-connectable advertising, that it will just advertise. Discoverable advertising, which the central may request more information and peripheral can send data without connection. So discoverable means you advertise that I am a thermometer, and then the central says, give me the temperature, and you give the temperature and you're gone. Right? So somebody can discover you and then ask you. General advertising. Broadcast pre-sends wanting to connect, and central may request a short connection. Now this is more than one message. This is closer to the old Bluetooth, where you say, look, I am a file system and I want to send something, or maybe I'm a headset, I don't know. I want to send something, and so central may say, okay, all right, let's make a connection, and then let's do some data transfer, and then we disconnect. Okay? You don't have to sleep or anything like that. Basically the connection is active, and then you are done, and you disconnect and you're gone. So even here, there is no inactive connect. Understand that difference? So basically you connect for activity, and that is optional too, right? General advertising. Third is directed advertising. So directed is that this particular packet, this is an announcement, but this is going to my master, or whoever basically I connected before, which is actually the master or central. So it will say, okay, so say for example you have something private that you don't want everybody to see, so you are going to encrypt it. And that one is basically, it's just one message. Thermometer says 37 degrees encrypted, but it is for this station. That station listens to it and is happy with it. That's it. Nobody else knows the keys. If they listen to it, they can't figure it out. Right? So there are four kinds of advertising. One more time. Clear advertising, discoverable advertising, general advertising means connection for connection, and then directed means confidential. So after, if you want to do a connection, so I mean, if you do need to do more than one message, then in that case the master will tell you the slave. Actually, I should change this word here. The central change the peripheral. Well, actually, here is what happens. I mean, they probably use mixed up language themselves. That's why I put the mixed up language here. Is that central becomes the master and the peripheral becomes the slave anyway. So anyway, the master tells the slave about hopping sequence and the wake up cycle, and all the subsequent data is done in 37 data channels. So if you have to do more than one of this pair of things, then it says, okay, all right, we will talk for the next whatever. And so here is my hopping sequence formula, and now here is my clock, and you synchronize, and then every so often the two will exchange. Everything is agged. So just like before, the original Bluetooth, the master will talk in the even slots and odd slots and things like that. So all that continues. Both devices can sleep between the transactions. So even the master can sleep. Data can be encrypted. Now, so this is all, this is all traditional method, but it is quite possible that many of the devices will operate in this method where they just advertise and go to sleep. They don't have to worry about any protocol business. Okay. For example, if you are running and you have some kind of running device, meter or something, yes, your partner, somebody else running next to you can listen to the same announcements. What is your speed? But why do you care? So you will just, leave it alone. Yeah.
In case where there is no connection, how does it make sure that the data is received?
There is no surety required.
So data may not be received as well.
I mean, when you put a thermometer on your wall, how do you make sure that somebody reads it? If they need it, they will read it, right?
Okay.
So the other end will say, I am not seeing any thermometer, what is happening, and then they will fix something, right? So it is not the responsibility of the thermometer to figure out that somebody has read it or not. The person who needs it will figure it out. If you suppose you have a heart rate monitor, just for the example, actually it will probably do better than this. If you don't get your monitor pulse for for a minute, there will be a big alarm going on saying that you must check your battery. This is the realization that came up with the Internet of Things, and that is so the next point here. So each transaction takes 3 milliseconds and takes 15 milliwatts of power. 15 milliwatt if you are using 1.5 volt battery. Actually, I checked, most of the batteries are 3 volts. But anyway, if you are using 1.5 volt battery, it will take 10 milliampere from that battery for 3 milliseconds. So that is about 30 microampere seconds per transaction. You take the milliampere, multiply by the seconds, you get microampere, because milli and milli become micro. 30 microampere seconds. The battery capacity is 180 milliampere hour. Simple coin cell battery, the one that goes into your watch, is 180 milliampere hour. Okay, that gives you 21.6 million transactions. And if you did one transaction per minute, it will last for 41 years. Obviously, this is an extreme. It will probably not last that long. Some chemical will go bad by that time. But the networking protocol is not to blame. Okay? So now all of you can do calculation of the battery life, right? Yeah.
The data are only used
Which channels? Data channels. Data channels are only used after, okay, no, hold on. In general advertising, what will you do is that you will use these 3 channels to advertise, but when you make a connection, then you will move on to the data channel.
Yeah.
And the directed advertising actually is not a connection. So this is so you made a connection and you transferred a whole file or whatever. That is all data channel, right? In the general advertising. And then it is quite possible that you are not really transferring a file, but you just now made a connection and then you went back to sleep, but you know everything else, right? So then you will do data channel here. Yeah, directed advertising. Now hold on. No. I'm wrong. All 4 advertising are on the advertising channel. So your question was, is the data channel used for directed advertising? No.
So what I mean is that the data are used being associated with certain types of.
No, data. Okay, so here, all these 4 messages are on the advertising channel. Even this data is on the advertising channel. This data is on the advertising channel. The data channel is only used after general advertising.
Only after check. What about the directed advertising?
Directed advertising uses basically this channel. Yeah. So advertising channel is for all these 4 kinds of advertising. And directed advertising is an advertising, except that it is directed to a particular station. It has an address. Rest of them are broadcast, maybe, some of them are broadcast.
So most of the time, only the 3 channels are used.
Yeah, that is true. I mean, most of the time. Now the question is, I don't really know how long is the data part. So hopefully there is not much data there. So most of the time, yes. Yeah. And they either hop, means random hop, or they cycle between the three channels. So when you say 37 degrees, you say 37 degrees on channel 37, then channel 38, and channel 39, just to make sure that everybody has somehow heard your advertising. Okay. All right. So that is Bluetooth Smart. Now this also has another protocol stack. Obviously, I don't have time to go through any of this. The main thing that I wanted to say was that they did change, and that is that they changed the profile. They put a profile called generic attribute profile. The reason is because in this case, you really don't want to design a profile for every application, and the number of applications is just growing. So they said, let's just design one profile that everybody can use. All right. So that generic attribute profile, GATT is generic attribute profile. All this is basically that you can send any data as long as it is TLV encoded. TLV is type, length, and value. So type is standardized by Bluetooth. So if you say this is data type 1444 and 1444 is heart rate, then anybody can understand that this is heart rate being advertised. 1323 temperature, then everybody can understand this is temperature. And so 16-bit UUID, 16-bit universally unique ID is standardized by the Bluetooth SIG. So all they standardize is the data type and not the whole application. Okay? And you put that data in your message, and the other guy will understand what is it that you are trying to say. If you want to have your own UUID, you can do so too. A manufacturer can assign a UUID which will be 128-bit. And obviously, some part of that 128-bit will have OUI, 22-bit assigned by IEEE. So that Cisco can assign its own, Broadcom can assign its own, IBM can assign its own. Everybody can put their own special data types. And then it allows any client to find a server, read, write data, and so now you don't have to worry about whether this is a headset or not. The thing is, previously a phone could talk only to a headset, and headset to say that I am a headset, and so on and so forth, right? Now A can talk to B, and you can tell them the temperature to B, and the B is a thermometer or not, who cares? What is B? Right? Anybody can talk to anybody because we know what data is coming. And if you don't understand the data, you ignore it. If you understand the data, make use of it. All right. So that is it is called generic attribute profile. And it allows security. So you could encrypt the data with AES 128. And you can encode the data or messages into XML. And so then now, the applications will, basically there will be too many applications. In fact, they assume there will be so many apps that they will probably open their own app store. Now I'm not sure about this, but I think they have opened their own app store. Everybody is going after Apple. So they have their own app store for Bluetooth. Okay. And so this is what smart is. This is what smart is all about, right? Now the gateway devices are important part of this whole technology. So your iPhone is a gateway, for example. If somebody wants to know what time it is, they could talk to your iPhone. Or some data you want to publish on the web, they could talk to your iPhone, and iPhone could put it on the web. Or the device could tell you where to put it on the web. Generic attribute profile, it could just tell the iPhone that, look, I want you to put this temperature at this URL. Now hopefully there is some security in between, and then it will go to that URL and put it there. Yeah.
Smart Bluetooth is the VNET like the older stuff?
Yeah. Sorry, what was your question?
Does this version of Bluetooth use the encapsulation like the older stuff?
No, actually the thing is, I don't know whether I can answer that question, but this stack was the previous stack, which is very different from the new stack. So the new stack does allow you to go to IPv6. However, where is the method for, I thought the method for going to IPv6 is actually under development. So I really don't think right now it is there. I think right now the way to get to IP is to this device. So this speaks Bluetooth, and then after this Bluetooth is forgotten basically. How the data came here is forgotten. From here you speak IP. So applications, the key applications are proximity. So if I put some kind of these stickers on the wall, in the room, in the car, and every place, then my iPhone will know where I am. It will know I'm in room 233, I'm in Lapata 401, just because Bluetooth will tell them. You can put those stickers on your keys so they can tell you which room they are in. If you want to find your keys, so they sell those stickers. You want to find your animals, your watches, anything valuable, your kids, health devices. Health devices, obviously heart rate monitors, physical activity monitors, thermometers, sensors of any kind, temperature, battery status. They could also tell you that battery is low on anything, like for example, if you have a smoke detector, Bluetooth could tell that you have to replace your battery in the smoke detector. Remote control, same thing, Bluetooth remote control rather than infrared remote control. You could turn on the lights as you walk into the room, right? All that. Now there is one interesting application which has come up called beacons, invented by Apple. Basically, if you walk into a store and you start looking at something, the beacon could tell you this is Mr. Raj Jain and he bought last time this and that, and it could give me right away advertising exactly tuned for me. Here is a $20 coupon if you buy it today right now. Okay. So there will be these stickers all over, we said on the wall, no, there will be stickers all over the store which will figure it out who I am, where I am. My whole itinerary will be tracked. How much time I spent. If I stop someplace, I know they know that I'm interested in this thing. Next day I will get a coupon in the mail. So this is called iBeacon. And so these broadcasts allow devices. Remember, advertising was to allow devices so they can find, where your phone is, where your key is, but now they can find where you are. Right? As soon as you walk into the store, your Bluetooth tells the store that, okay, this is the guy, and they fill out the whole history and start talking to you everything that you wanted to hear. And iOS 7 can send and receive beacons, can be used for customized advertising and and then you can use it for door location if you want to find out where you are, your kids are, this is a good thing. Geofencing, where your dog is. And PayPal uses this even for payment. To make a payment, you just put your phone and plug some numbers in. Bluetooth advertising gives it to them and they're done. So anyway, beacons are coming, and I don't know. This actually caused me a little bit worry, but I have to turn off my Bluetooth now. The only time I need Bluetooth is in my car. If I'm in the car, if somebody calls, if I want to make a phone call, that is an application where I cannot live without Bluetooth. Other places I can live without. I don't use the headsets and things like that, but the car is important. But anyway, that brings us to the end of Bluetooth lecture. Bluetooth basic rate, we know 5 key points. First thing is that it has used 79 1 megahertz channels, and the slots are 1, 3, and 5 slots long, and the packets are 1, 3, 5 slots long. Then there are 3 inactive states. So they tried to make a very energy efficient protocol which had 3 states: hold, sniff, and park. Sniff is that you're connected but sleeping. Park is when you are really, deep sleep. And and hold is when you just go on to do something else. And they had applications which were completely logged in called profiles. Then they designed a coexistence strategies, so you really never felt that you had two kinds of devices using the same band. Fourth thing, now the Smart has come in, which allows short broadcast. It's very simple. But uses 39 2 megahertz channel with 3 channels reserved for advertising. And this is really low energy. And then there's a profile also which is very general, so any kind of application. So we are going to see this really mushroom of applications for Internet of Things using Bluetooth Smart. And the thing that they're really getting on is the name Bluetooth. See, name Ethernet. If you sell the same protocol with a different name, it will not sell. So I remember when we did work on something called FDDI, Fiber Data Distributed Interface. It is 100 megabit. How do you get 100 megabit over the fiber back in 1984? Nobody bought it. But we changed the name to Ethernet 100 megabit. Believe it or not, this is the fact. Just the name change. Same technology. Change the name to Ethernet 100 megabit. It sold like hotcakes and it is still sold today. Okay? Bluetooth Smart would not sell if you call it something else. But Bluetooth is known. Everybody knows Bluetooth. Old one, right? So the Bluetooth Smart can sell an incompatible technology like that. And people will buy it as compared to the competition which we are going to discuss in the next lecture. Zigbee and other things. They don't have the name recognition.